Hello everyone, welcome to another competitive programming video. Today we're looking at the problem kth nearest, which was problem D in Atcoder Beginner Contest 364. So the question reads that we're given n plus q points. The points n will be from a1 to an, and the points b will be from b1 to bq, and these points are all on a number line. So point ai has coordinate ai, likewise bj has coordinate bj. So for each of these elements in Q, what we want to do is the following. So we want to let X be the point along all the 8 points that is the kth closest to B. So what that means is we're given a point B, and we want to find the point that is the kth closest to that point. So when we go into the example, this will make a bit more sense. So basically what we're doing is for each query here, we want to find the kth closest point to B. So let's look at an example here. We have the points -3, -1, 5, and 6. So our first query says the point -2 on this line, let's find the third closest point, or rather the distance to the third closest point. So we'll see that from -2, the third closest point is 7, and this represents the distance for all those points. For the second query, the distance to the first closest point is 3, and for this query 4, the distance to the fourth closest point is 13. So the problem statement's kind of confusing, so let's hop over into an example a bit closer and see exactly how we can solve this. So let's take a closer look at this example. So we have these points on our number line, and let's actually draw it as a number line to make it a bit clearer. So we'll have -3, we'll have -1, we will have 5 over here, and then 6 over here. So for example, our first query here says, find the point -2 on this line. So let's have that right here. This point doesn't actually exist on our line for our intents and purposes. We're just going to mark it here for visual ease. And then we want to find the third closest point to this -2. So we can see that these are both 1 away, right? So we could say that -2 and -3, distance of 1, -2 to -1, distance of 1. So the third closest point is this 5, and this to here has a distance of 7. So 7 is what we want to print out for this query. So how do we actually solve this? Well, you might notice that this is sorted, right? So you might think, well, let me find -2, and then we can go through k elements, with k being this, until we get to the number k, and we can return that. So what would that look like? So say we're here, we want to go through 3 close points. So we'll say, all right, either of these could be the first closest one. So let's eliminate 1 so we can cross this off. So now we've gone through 1 point. So now let's look at the next closest. The next closest is 3, so we can do that. And then the third closest would be here. So basically what we're doing is we're starting from a point, we're looking to our left and right to see which point is closer, eliminating that, and then kind of moving our pointer to either the left or right, depending on what we eliminate. So this was kind of my first intuition, but the issue is that we could have a q value here, like a k value, that is almost equal to n, or actually equal to n. So that means we could be doing, for each query, we could be doing n work, right? And q can also be the same size as n. So this actually is O of n squared. So with this solution, we'd be doing O of n squared. And this is just not going to pass. It's way too slow. So you see here, we're kind of framing this as we're trying to count the points, right? We're finding the closest point to what we're looking for, and then we're kind of eliminating points as we go. But if we actually reframe this a bit, it becomes a bit easier. So what if instead of going to the individual points, we find the smallest distance away from this point that contains k number of points? I'll say that one more time. If we have this point here that we're looking for, this is the point that we're starting our query from, we want to find the distance from this point that has the number k, the smallest distance from this point that has the number k. So you could say, all right, so let's start at -2, and let's say we extend our sides by 1 to start, right? We'll say, does this have k points? Well, no, this only has 2, right? So we need to extend again. So we'll say we'd come to -4 and 2. This still has 2, so we would need to extend again, right? We need to go to -5 then and 3, or yeah, -5 and 2. So you can see like we're kind of extending outwards, so until we get to a point where we have 3 points enclosed. So this could work, right? We're just going to extend our left and right until we get those 3 points, and that's guaranteed to be the smallest point. But again, we're still going through basically n elements. Technically, we're cutting it to n over 2, right? Because we're only doing like pairs of elements, but this still cancels out and would equal n. So again, this is still too slow. So one thing you might notice is that we're going through in a sorted way, right? We see that this number line is technically sorted, and what you can see is that we started with 1 distance, we started with 2 distance, then went to 3, then to 4, then to 5. So we're going up incrementally. And anytime you see that we're going through a search space like this and checking for a condition, we should be thinking of binary search, right? And the reason this is because technically the search space we're sorting through, distance from 1 to some n value, right? This is sorted in ascending order. So we could take advantage of binary search to cut our search space in half at any given point. So how would this actually work? So you can imagine the smallest distance that we could possibly go from 2, and let me go down a little bit so we have more room. The smallest distance we can go from 2 would be 0, right? And the highest distance we could go, let's say, for our intents and purposes, is pretty large. It's like 10 to the 8. But let's just say for this case, we're going to deal with a small number. Let's say 50. So what we want to do is say, let's take our midpoint. Our mid equals 25 here. And we're going to say, let's look 25 this way and 25 this way. So here we'd come all the way over here to 23. And then this would be -27. So we'll see in this range here, do we have 3 points? Well, we do. We actually have 4 points. But remember, we're looking for the smallest, right? We're looking for the smallest possible distance that has 3 points. So we could say, all right, well, we know this satisfies it. So let's then shrink our window that we're looking for to find an even smaller one. So what we can do is say our right now becomes 25, right? Because this left to right represents the distance away from our point that we're looking, and we know that we want to shrink that distance. So now our mid becomes 12, right? So now we have 12, we can go up to 10 here, and then -8 here. So again, we see that this contains 4 points. So again, we know this is valid. Let's look for a smaller one. So we're going to make, again, our right equals 12. And then what we do is we say our mid is 6. So now let's go from here. So again, we go to -8. I computed wrong last time. Should have been -12. But then we go from -2. We go to 4, right? So +6, -2 is 4. So we'll see that here we actually only contain these 2 points. And this means that we have to actually increase the distance that we're looking for, right? So we need to say, all right, we know that it's not 6, so our left has to become 6 because we're looking for a distance in between these two. So you can see how we're applying binary search. Let's go through the rest of the steps. So 6 divided by 12, this will become 9, right? So we'll have -2 plus 9, this is 7, right? So we'll have 7 here, and then -2 minus 9 equals -11. So we'll see here, this contains all 4 points. So what we want to do is we want to shrink our right again. So this becomes 9. Then what we can do is we'll say the mid here, 6 plus 9 is 15 divided by 2, which is 7. We'll say, all right, let's go 7. So here we see -2, we come to 5, right? So 5 here is where we're ending. And then we come here, -2 minus 7 is -9. So we'll see this contains 3 points, right? It's on the boundary, but technically it contains 3 points. So we're going to say, okay, so this is valid, but let's try to find an even smaller search size to see if this is our minimum. So what we can do is we'll say our right is equal to 7. So now at this point, we're getting very close to the end. Let's delete these. And what we can do is say 6 plus 7 is 13. divided by 2 is 6. So our midpoint is 6, right? So then what we can do is negative 2 plus 6 is 4, and then negative 2 minus 6, negative 8. So see, this again only contains 2 points. So what we need to do is we need to make our search size larger. So we eliminate that, and we see our left is again 6. So we can use this condition and say when these are 1 away from each other, that means we've reached a terminal condition, right? And at this point, we know that we can't go anymore. We're just going to be in an infinite loop. We're just going to get the same result over and over. So see, at this point, we get to that result, which is 7, which is what we knew we were looking for this query. So essentially what we're going to do is we're going to apply a binary search, and we can either do it in one of 2 ways. We can update our boundary to be the middle, right? So we see that 6 is equal to our left here, and we've the whole time just been updating the boundary to be exactly our mid, or we can make the left and right plus 1 or minus 1 of our mid, which will change exactly how we would check for our boundary and stop our iteration. So I'll show that when we get to the code, the different options there. So what's the time complexity of the solution? So we're still doing Q queries, right? But for each one, we're only doing log n work. So this is much, much better than the O of n squared that we saw before, right? So you can see that in this case, we're using the fact that this is in sorted order that, to use binary search and be able to efficiently find our solution. So let's hop over to the code and see exactly how it works. So the first thing we do is we import some functions from the bisect library. So bisect and bisect right are 2 separate functions. Bisect is going to take a target and find a value to the left in our sorted range of that target. So if we give it like 5, it will say find 5 or an element to the left of that. And likewise, bisect right will do the same thing for the right. And we use this to find the lower and upper bounds from the distance at any point. So then we take in our n and q values. We also take in our a, and we're going to sort our a to ensure that it's in sorted order, and we can apply binary search on it. So then for each query, we're going to take in our b value and our q value, and then we start our binary search here. So what we then do is I'm using the condition while right is greater than or equal to left. And this is a condition where we have to make sure we're decrementing or incrementing our mid by 1, or else we're going to run into an infinite loop. So what we do is we just take the midpoint, we find the lower and upper bounds, and the lower bound being in A, we want to find B, the point we're querying for, minus the mid that we found, minus 1. So this is going to be the lower bound. So you remember from the example, if say our midpoint is 6, we're going to the left of our point by 6 and then to the right of our point by 6. So this represents the left point, and likewise this represents our right point, where we're going B plus mid. So then we're going to check our condition. If our upper bound minus our lower bound is greater than or equal to k, and what this means is that we have greater than or equal to k points at this current distance. And if this is true, it means we have to look for a smaller distance. Otherwise, it means that we don't have enough points. We don't even have k in our current distance, so we have to increase that distance by 1. And then what we do is at the end, we're just going to print out our left value. So let's paste this code into Atcoder and make sure that it actually works. Submitting now. Here you'll see it's waiting to be judged. And finally, we see that our solution was accepted. So this is a pretty cool binary search problem. Hopefully the explanation made sense, and thank you for watching.